class, I just have a couple quick comments about the assignment you guys are going to do for 2.2b. Really, it's just a review of what you learned in Chapter 1, but we're just applying it to the power functions that you learned about yesterday. So let's get to it. We have a function here that is negative 2x to the negative 3. It is a power function, and we want to identify the power and the constant of variation first. The power is negative 3, and then the constant of variation is negative 2. Okay, so negative 3 for our power, negative 2 for the constant variation. Okay, then after that, we want to graph it, and you may use Desmos.com to graph. So if I go over to Desmos.com and graph it, it's going to look like that. Next, we want to analyze. Now, when it says analyze, it sounds like such a harmless word, but holy cow, analyze means tell me every single thing you know about the graph. So you're going to take everything you learned in Chapter 1 and start writing about this function. So let's go through some of the things that you should be able to say. First one, domain. If we move a vertical line from left to right, and then we say, when are we in contact with the graph? We're in contact, lose contact, in contact. All right, so we are in contact as we move that line across until we get to x equals 0. We lose contact momentarily, and then we're in contact again. So the domain is negative infinity through 0, union 0 through infinity. You should be able to look at a graph to determine the domain. If I did, however, rewrite this, it would be negative 2 all over x to the power of 3, and we can't have x's in the denominator. Those could cause us some domain issues, and if you did set x to the third power not equal to 0, you would also find out that this does not, the x cannot be 0. Okay, the range, similarly, let's just run instead a horizontal line from the bottom to the top. And as we move that line up, we stay in contact with the graph until we are at the x-axis, and we lose contact momentarily. And for the range, we're thinking about the y-axis. So at 0, we lose contact. And then as soon as we get past the x-axis, we're back in contact. All right, so our range is also going to be negative infinity up to 0, leave out the 0, and then after 0 through infinity. We should be able to tell where the function is increasing or decreasing. All right, so taking a look, see as we move across and follow this, we're going up, 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 up. All right, then here, if I jump on anywhere we want, and then I start moving across, we're going up, 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 up. And even right here, it kind of looks like it's straight across, but it's not. It's getting, every point is a tiny, tiny bit higher than the one that came before it. So it's also increasing there forever. So we are increasing from negative infinity, think about the x-axis there for interval notation. So from negative infinity until we get to here. We can't include x equals 0 because there's no graph there. And then right after 0, we're going to start increasing again forever. So increasing from forever to the left until we get to 0. And then right after 0, we're increasing forever to the right. Right, decreasing, we don't have any intervals where we're decreasing, so I'm just going to say no. Symmetry could have symmetry with respect to the y-axis, or we could have symmetry that's to the origin. Notice no matter what point I go to on the graph, I'm just going to randomly go right there. If I go there and I jump across the x-axis and then I reflect across the y-axis, see how I'm back on the graph? That's true for every single point here. So we do have symmetry to the origin because this function is odd. All right, next, boundedness. Can we put a ceiling and ensure that the graph stays below it, or can we put a floor and ensure that the graph stays above it? Well, we cannot put in a floor because this is going down forever. We cannot put a ceiling because it is going up forever. So it is not bounded above or below, so not bounded. Local mins and maxes. Remember, the definition is if your function goes from uphill, increasing, to decreasing, that's where you have a local max. Or if your function goes from decreasing to increasing, well, then that's where you have a local min. All along the way, I have increasing, 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 increasing. So we definitely don't have any places where we're changing from increasing to decreasing or decreasing to increasing. So we do not have any local mins or maxes. Asymptotes. Oh, we got a couple of those. Y equals 0. That is the equation for the x-axis. All right, so y equals 0 is our x-axis. That's definitely an asymptote. And then also x equals 0. The y-axis, the equation of the y-axis is x equals 0. Lastly here, discontinuities. The layman's definition there of discontinuities is if I start drawing this function, am I ever going to have to come to a spot where I have to pick up my pencil and put it back down to be able to continue drawing? So yes, I can jump on anywhere I want. It goes forever to the left. I start drawing. For me to finish this picture, I'm going to have to lift up my pencil. I'll go to the other side of the asymptote, and now I can continue drawing, and I won't have to lift up my pencil again. So we have a discontinuity at x equals 0. All right, so one more time, we are just going to grab our graphing calculators or Desmos.com. We're going to graph the function, and when it says to analyze, you want to include all of these pieces. So there's really not anything new, it's just a quick review. All right, this is our last lesson before heading into the weekend. I hope you guys have a great weekend.